So, thanks. All right. So, chapter 12, which is kinetics, I think, is what we were talking about here. So, remember, as we talked about last time, kinetics deals with really how fast or slow a reaction is taking place. As we talked about as well, thermodynamics, which we'll talk a little bit more about later on in the semester, deals with the idea of whether or not a reaction will take place. But really, kinetics deals with sort of the rates of reactions. And we talked about a couple of things with kinetics. We talked about what's sometimes referred to as the rate expression. And the rate expression can be written from an equation. And we could say that the rate is equal to minus 1 over 2, the change in the concentration of A over the change in time. And that equals minus 1 over 3, change in the concentration of B over the change in time. And that equals 1 over 2, change in concentration of C over the change in time. A couple important things that we talked about was since our reactants in this reaction is heading in this direction, we would expect our reactants to decrease with time. We would expect our products to increase with time. Yeah. What's that? Yeah. So it is sort of like what the names imply. So disappearance means what is sort of decreasing with time. So for example, in this reaction, we would expect the reactants to start to disappear. So sometimes it may be referred to as the rate of disappearance because it's a reactant in this case and it should be decreasing. While the product should start to be made, basically, and that would be sometimes termed the rate of appearance and stuff like that. Yeah. Other questions? So as we talked about, because reactants are decreasing, we do include the negative here when we write these rate expressions. And that is because when we do the change in the concentration, say, of A, which is basically the final concentration of A minus the initial concentration of A, because it is decreasing with time, that's going to yield us a negative number along with this negative. We'll once again turn our rate into a positive number, which it typically is. And that is really sort of the average rate for the reaction, as we talked about. Now, we also, in this case, take 1 over the coefficients. And the reason we take 1 over the coefficients is, as we talked about, that sort of does the stoichiometry part of the calculation, along with the kinetics part of the calculation, which we also saw, I think, in that very last example. You could do the stoichiometry part first and kind of incorporate all the kinetics part at the end, but this kind of does it all together. So taking that 1 over the coefficient allows you to get the correct really mole-to-mole relationship that's happening in this reaction. And we do not have that over here on our product side because, again, the negative is for our reactants, so our product should be increasing. So when we do the change in the concentration of our product here, we would expect a positive number to occur because it's going to basically be increasing with time, and that will give us, again, our positive rate. As we saw in some of those examples that we did, you could really just kind of pull each of these things out for whichever ones you're interested in. You don't have to set the entire thing equal to each other. So if we were just to maybe interested in these two guys here, we could write two kind of separate rate expressions for A and C. And as we talked about, what really ties these two together is basically this number here. And that's the one that allows you basically to relate whatever information they give you to everybody else in the sort of reaction. So as long as you have basically one piece of information like a rate, how somebody is decreasing with time or increasing with time, you can basically relate that to everybody else in the equation through these sort of relationships here. Now, remember that if you do solve for, say, something like this, which is a reactant, and you're interested in how that reactant is changing with time, you will end up with probably a negative number for that because it should be decreasing with time, as opposed to if you solve for C here, for the change in concentration of C over time, that would yield you a positive sort of value as well. I think we also talked about factors that come into play in terms of the reaction rate. And remember that things like concentration, so the higher the concentration, the more availability for the reactants to start reacting basically with each other. And that usually will increase the reaction. Opposite is true, lower concentration, less availability of everybody swimming around and say the solution to start reacting. Temperature as well plays a really big role in terms of the rate of the reaction. When we increase the temperature, we increase the energy. That allows more molecules basically to have enough energy to get up and over sort of the activation energy hill to the other side. It also allows a greater proportion of molecules to have enough energy when they do collide with each other to get that reaction sort of going. And the opposite, right, is true. If we did something like lower the temperature, we would have a lower proportion of molecules that have enough energy to get that reaction going, and that usually will sort of slow down the reaction. We could also add a catalyst as well, and as we talked about, a catalyst is not a reactant, not a product. It doesn't get used up in the reaction. It is there really just to facilitate sort of, again, that reaction happening more efficiently, I guess is a way you can look at it. And by doing so, it creates sort of an alternative pathway for that reaction to take place, one that is a little less energy dependent. And because of a little less energy for that reaction to take place in a catalyzed reaction, it actually will lower the activation energy and allow more guys to get to the other side a lot quicker, and usually will increase the rate of reaction. Any questions on any of that stuff there that we talked about, I think? Yeah. All right. So I think my memory serves me correctly. We laid up here. We didn't start this one, right? So we'll go here. We're going to talk now about the rate law. And the rate law expresses the relationship of the rate of reaction to its rate constant and the concentrations of its reactants to some powers. So this is, if we have this equation here, this is a generic sort of rate law. This is the rate, like molarity over seconds. This is our rate constant. We have the concentration of our reactant, A to the X and B to the Y. Here, X and Y are what are referred to as being the orders for those particular reactants. And if you want the overall order for a reaction, you could add basically X and Y together, and that will give you your overall order for a particular reaction in this particular case. Now, one of the important things about a rate law and a little different than a rate expression is it's all about reactants. So there are no products typically in a rate law. It's all about really our reactants and what's happening with our reactants. Also, are typically found experimentally. They are not necessarily the coefficients that you see in the balanced equation. So we do not use the coefficients for those exponents, the X and the Y. We actually find them experimentally, as we will see, which means usually you'll be given a table, a bunch of stuff you use to calculate those orders. So what is this? What does a rate law sort of tell us? And what do these orders sort of tell us? It's again sort of the proportion of each of these reactants that's necessary for this reaction to maintain a specific rate. And what is sort of the benefit of, say, knowing the orders, knowing the rate law is you can, use it to your advantage in certain cases. So for example, here, let's just say we had concentration of A was 2 molar, concentration of B was also 2 molar. And let's say rate law where the rate is equal to K times A times B. In this case, much like most things in chemistry, if there's nothing written on top, it is assumed to be 1 in each case. You don't need to write the ones typically. That means that the overall order here would be found, by the way, by just adding those together. 1 plus 1 is a second order reaction overall. So let's say we did this reaction and we threw our concentrations into this rate law, And since K is a constant, it doesn't really matter too much. So we would have something like the rate is equal to K times 2 times 2, which will essentially give us something like 4 molar, we'll call it seconds. Again, the rate constant is going to stay the same no matter, what it is for this particular reaction. So let's say that you did this reaction and you go, wow, that seems a little quick, or not quick enough. And let's just say that for B, I decide in this next reaction that I do, I want to increase the concentration to 4. So for example, here, if we did that, the rate would equal K times 2. And now I'm going to increase my concentration of B to 4. This will now essentially give me a rate of 8 molar seconds. I doubled, right, the concentration here of B. The rate actually did what? It doubled as well, yeah? So this would be a case of maybe this reaction is running too slow, right? I could just increase the concentration of B. That will get this reaction to basically go twice as fast. In this case, I could also do the same thing with A and keep B the same and raise the concentration of A. It would result in sort of the same thing. Let's say, for example, though, you did this reaction and you're like, whoa, way too fast for me to record, which can happen. Like some experiments we'll do later on the semester, if you're a little slow, you miss the entire reaction by the time you get it into like the spectrophotometer. By the time you're there, the reaction's over. And so sometimes you might need to kind of slow down a reaction and stuff like that. So let's just say that instead of doubling my concentration of B, I decide I want to cut it in half. So if I did that and threw it into this rate law, we would have 2 times 1, right? Which will give us something like 2 molar seconds. By cutting the concentration of B in half, what happened to the rate of this reaction? Just slow down by half, right? So I could slow it down. So this is really sort of a practical application of understanding the rate law for a particular reaction as to what things have an effect on the overall rate of that reaction. You can play with the concentrations to change the rates if you need to. And it is dependent. So what would happen in this case if we started with a rate law that was K is A and B is to the second here? The overall order for this guy would be 1 plus 2, which is a third order reaction. And you get that by adding the orders, the X and the Y's together, basically. So now if we did our original sort of setup here with 2 molar of each of these guys, when I put it into here, I basically will get 2 times third. That's going to give me an 8 molar seconds, right? And just using the same concentration as the first rate law, we actually have a twice as much, right? Because of the B's contribution here, right? And now by changing B in this particular reaction, we'll actually see probably a bigger sort of change. So let's say we did double the concentration of B in this case. So we would do our 2 and then double this to 4. It would be squared. So 4 squared is 16, I think, times 2 is like 32, I think, right? Now by doubling B in this particular reaction, my rate went up by a factor of 4, right? 32 divided by 8 is 4. Yeah. So a factor of 4 by just doubling the concentration of B, right? If I doubled the concentration of A in this case, but kept B the same in this reaction, we would have 4 times 2 squared. That would give me 16 molar seconds. My rate went up, right? But it only went up by a factor of 2, right? So in this case, the one that has a greater effect on the rate is which concentration? B, right? B is definitely the one that has the bigger effect on the concentration. As when you play with B, it will have a bigger effect because it has a second order. So these are sort of what the orders sort of do. They have a relationship. Not the spider again. Is this the spider again? I love that. All right. What is called our pet spider? Is it okay? Yes. Same one. Well, I'd hope so. I don't sound like a whole new breed of spiders in here. Yes. I'm going to keep K a constant. It is a constant. So in any of these ones, it'd basically be the same number, right? So its effect on the overall rate is going to be basically the same no matter. So it's really the concentrations here that are changing. And technically speaking, that's sort of where our time part would come from, is the rate constant part of it. So I'm just kind of putting that in as well. But since it is a constant, it won't have an effect. So here B would have obviously a greater effect. And now, for example, if we were to cut our concentration of B in half, in this case, we would have the rate is equal to 2 times 1 squared, right? Which is now a rate of like 2 molar seconds. So our rate in this case actually went down, right, by a factor of 4 as well. So knowing the rate law, knowing the orders, some reactants may have a greater impact on the overall rate of that reaction, depending on their order in there. Any questions on that there? What happens if I had a rate is equal to K, A, and B to the 0? B to the 0 equals, or anything to the 0 power is 1. So in this particular case, the only one that really affects the rate is which concentration, A or B? It is A, right? Because you could do as much as you want to be. You could raise it to like 400, but when you take 400 to the 0, it's going to always end up at 1. So you could do as much as you would want in that particular reaction to be. It will have really no effect on the rate because of its 0 order. So in this reaction, really the whole rate is all determined by what's going on with A in this case. Any questions on any of that there? All right, so yeah. So in this first, we'll go summarize the ones we looked at. So in this very first one, since they were both really first order, they both will have sort of an equal effect, right? So even though we did double B in that one, if we doubled A, you would get the same result of it going up or down because they're both first order. When we went to this one, they both, again, A and B would have an effect on the rate if you did something to either one of them, but B would have a greater effect because it's second order. So when we doubled B, our rate went up by a factor of 4, versus when we doubled A and kept B the same, our rate only went up by a factor of 2. Yeah. No, you mean these twos are like this two? The two I just circled? Oh, right here?
Yeah.
Are just where it says 2 molar? I just made up the numbers for 2. Yeah. It's just I tried to take a nice easy number like 2, seemed like a good number to use there. So it's just a made up number, the more stuff like that. Yeah. Other questions? So again, and then obviously in this last one, as we talked about, really the only thing that could affect the rate, as we said, is A. Again, you can do whatever you want to be. It's going to have really no effect on it. And usually when we write the rate law, if it is 0, we don't necessarily need to even include it in the rate law. And you would have just like A by itself, basically, in that case. All right, so now we sort of understand, hopefully, a little bit about the rate laws and sort of the effect of it. Let's talk about how we actually calculate the rate laws for a particular reaction. So this is a typical table that you're given. So you'll be given the equation usually, and you'll be given this sort of experimental table. So since rate laws are found experimentally, you have to look at these tables. And typically in these tables, you'll see a couple of things or a few things listed. You will see the concentrations of your reactants. You'll also have some initial rates for each of these guys. And you'll have some different experiments. So this is like experiment 1, experiment 2, experiment 3. So these are 3 different experiments that were done for this reaction. And you measured basically the initial rates and the concentration of your reactants. I'm going to talk about the way that you can use this information to figure out the actual rate law. And I'm going to do more of a mathematical approach because that's usually best for people. If you understand sort of relationships, you could sort of figure out it without doing the math, but probably the math is a safer way to go. So the way we're going to do it is sort of mathematically, which is we're going to basically use this sort of formula here where it is the rate 2 over rate 1 is equal to K A to the X and B to the Y. And obviously, if you had more reactants, you could do more if you like. So let me tell you what each of these things means. Rate 2 and rate 1 does not mean that you just go to the table and you pick entry 1 and entry 2. It means that you actually just go to the table and you're going to find 2 entries. And what we're looking for in terms of our entries is one where one of the reactants concentration stays the same in both of the experiments and one varies. The idea there is we don't want more than one unknown at a time. So that will keep us just having kind of one unknown at a time. We can, by the way, for this equation that we're looking at, write the generic rate law of the rate is equal to K times F2 to the X and ClO2 to the Y. And again, we're going to use the table here to figure out what X and Y is. All right, so when we go to do this, it really doesn't matter which reactant you start with, but I'm going to look at the table, and what I see here is when I look at experiment 1 and experiment 2, the concentration of F2 stays the same. And so those are the 2 I'm going to choose here. The concentration of ClO2 does vary. So I'm going to look at experiment 1 and 2 here. And I'm going to look at my rates, and you don't necessarily have to do it this way, but a lot of times if you sort of do it this way, it will kind of give you nicer whole numbers rather than decimals, which sometimes is a little bit easier to visualize what's going on. So I would personally choose the experiment where once you choose your 2, the one that has the larger rate, I would put up on top, and that will give you more whole numbers than decimal type numbers. So in this case, the second entry has the larger rate. So what I'm going to do is take my second entry here, and I'm going to put it all into basically the top part of this equation, which means I have 4.8 times 10 to the minus 3 is going to equal K times the concentration of 0.1, and that's going to be to the X, times the concentration of 0.04 to the Y. So everything that I just put in here is all experiment 2 information into the appropriate sort of spot here. Now what I'm going to do is put everything for experiment 1 into the appropriate spot. And I'm going to do this, which will give me 0.1 to the X and now 0.01 to the Y. So once again, everything up on top came from experiment 2. And everything on the bottom came from experiment 1. Any questions on that so far? All right, so now we're just going to do some math. And again, by kind of putting the larger rate up on top, that in a lot of cases will give you a blank screen. No, that in a lot of cases will give you a whole number here. So I'm going to take 4.8 times 10 to the minus 3 and divide it by 1.2 times 10 to the minus 3. And when I do all that, I hope that is a 4. Yeah. Now that's going to equal coming across to the other side. This is a rate constant on top, right? That is a rate constant on the bottom. That is also, again, a rate constant. So should it be a different number or the same number? Yeah, that's the idea of a constant, right? So it's the same number there. So although we do not know what the K value is right at this moment, we do know the bottom one should be the same, which means they're going to cancel out. This is the order for our first reactant there, F2. That is the order for our first reactant, which is for F2. Although we do not know the order of X at this point, should it be the same or different numbers? Should be the same, right? It's the same sort of reaction happening in this case. So although we don't know it, we do know it's going to be the same, which means those guys are also going to cancel out as well. It's good canceling out. We're going to take 0.04 divided by 0.01, which is going to give me a 4 to the y. Yeah. And you could probably now see with these nice whole numbers that y equals 1, right? 4 to the 1, right? By the way, if you don't have pretty numbers or you're not sure, the proper way to do that, or one way that you could solve it, is you could take the natural log of both sides. And when you do, the y will come down, and then divide the natural log to both sides. So just in case you don't get really pretty numbers sometimes, which does happen in experiments and stuff like that, you basically could natural log both sides and divide it out to solve it. But a lot of times you could almost kind of, especially with a lot of textbook type problems, you could almost just kind of see the number and stuff like that. Again, if you did it the opposite way, where maybe you did the smaller rate up on top, you might get a decimal, so then you might want to do the natural log because you might not be able to maybe see maybe the numbers and stuff like that. But it should come out the same regardless. Any questions on that so far? All right, so now that we figured out what y is, what we're going to do now is go back to the table, and we're going to do the same thing, except in this case, we want to keep ClO2 constant and vary the F2. So we want to go back to this table. Get rid of all the stuff I scribbled on here. There we go. And we're going to look for two entries where the ClO2 stays constant and the F2 sort of varies. And in this case, that looks like experiments 1 and 3 will achieve that. And we're going to do the exact same thing. In this case, it looks like experiment 3 has the larger rate. So I'm going to put everything for experiment 3 up on top. We're going to do a 2.4 times 10 to the minus 3 equals 0.2 to the x, 0.01 to the y, divided by, and there's a k in there, our number 1, which is 1.2 times 10 to the minus 3, our k, 0.0, 0.10 to the x, and 0.01 to the y. So once again, here we're going to do our same sort of math. When we divide these guys out, that gives us a nice 2. Once again, the rate constant should be the same. When we divide the next thing, we do get 2 to the x. And once again, we already know that's 1, and those guys are going to cancel out. Once again, here, you could probably just see it. In this case, x would equal 1 in this case. So the order with respect to F2 is 1, our first order. The order with respect to ClO2 is first order. We can now write the completed rate law, which is the rate is equal to K times the concentration of F2 times the concentration of ClO2. The overall order for this reaction is going to be 1 plus 1, which is each of the orders added together, gives us a second order. First off, any question on that calculation there? Now that I have calculated the orders and I have the completed rate law, I can now use this table and the completed rate law to actually figure out what the value of the rate constant is. So we can now use our rate law to figure out the rate constant, and we do that by solving for K. And if I solve for K by rearranging our rate law, which is here, K would equal the rate divided by F2's concentration and ClO2. Where I get those numbers is the exact same table. Doesn't matter which experiment I choose, you think? It doesn't, because it's a rate constant, which means it should be the same for all those experiments, right? So you could choose all the information from experiment 1, you could choose the information from experiment 2 or experiment 3. The only thing you can't do is mix and match. So you just got to choose one. So here I'm going to choose experiment 1's information and put it in. And when I do that, I will get 1.2 times 10 to the minus 3 molar seconds divided by 0.1 molar divided by 0.01 molar in this case, right? And if I do all that good stuff there, 1.2 exponent button minus 3 divided by 0.1 divided by 0.01, I'm going to get a 1.2 as my rate constant. What are the units? Molarity on top and bottom cancels, still 1 over molar seconds. There's still molarity on the bottom as well, right? So 1 over molar seconds, or sometimes people write it m to the minus 1, s to the minus 1, same deal. And those are the units. It's really, really important to obviously have the units there for your rate constant. It's also really important as we go through this chapter, knowing the units of the rate constant can help you out because it will tell you the type of order that you're dealing with. For example, these are the typical units that you find for a second order reaction overall. And so sometimes, as we will see later on in this chapter, they won't with like blinking lights go, hey, this reaction is first order or second order overall. They will just give you the rate constant and they'll give you the units to go with it. And they assume by you seeing the units to go with the rate constant that you'll know what order of reaction it is. There's 3 really common orders that we come across in terms of overall orders. First order, second order, and zero order reactions are typically the reactions that we see. And just in general, when you think about reactions that take place or reactions that you've seen, most of the time you typically have 2 reactants, right? Or 1 reactant, right? Occasionally 3, but you usually don't get much more than that reacting. And if you just think about the different orders, in order to get really, really large orders overall for reactions, you need a lot of things reacting at once, right? And that usually is not the case. So usually those 3 are the common sort of overall orders, as we'll talk about in this chapter, first, second, and zero order reactions. Any questions on any of that there? So once again, this is a very common table. You want to first use it to get the orders of each reactant. Once you have the completed rate law, then you can use the table to figure out the value of the rate constant. All right. So as we see there, when we talk about rate laws, a couple of things important to keep in mind. And that is, again, rate laws are always determined experimentally, which means you will always have a table. And by the way, may have 3 entries, may have 4, may have 5, may have 6, may have 10. They'll have a bunch of entries sometimes. The reaction order is always defined in terms of the reactants. So again, usually our products are not included in the rate law. And the orders for the reactants are not based on the stoichiometry. So again, as we see in this case, the order for ClO2 is first, but in the reaction there, the coefficient is 2. So again, that is not where we get those numbers from. You got to actually calculate it experimentally. All right. So here, the rate equation for this reaction is of NO with ozone is the rate's equal to KNO times O3. If the rate is 6.6 times 10 to the minus 5 molar seconds, when the concentrations are those, what is the rate constant? So take a moment and calculate the rate constant here. See what you get for the units. Is the rate is equal to K times NO and O3. And in this case, by the way, the overall order here is going to be 1 plus 1, which would be a second order reaction overall, as again, each of those guys are first order. We're going to solve for K in this case. So K would equal the rate divided by NO and O3. So putting in our numbers here, 6.6 times 10 to the minus 5 molar seconds divided by 1 times 10 to the minus 6 molar, and 3 times 10 to the minus 6 molar, going to get us here looks like maybe like a 2.20 times 10 to the 7 in this case. Unit-wise, we are looking at molarity and molarity canceling, and that's again going to give us 1 over molar seconds in this particular case, which, as you can see, same units that we had for the previous one that was also second order overall as well. So again, knowing these units of the rate constant as we go through this chapter, really important to help you sort of determine things. Question on that there. Small rate constant, large rate constant? Pretty large, yeah. So pretty big reaction probably happening here, or rate's going to happen. Because if you think about it, right, you're going to multiply that number basically by the concentrations, which is going to give you a pretty big rate number, right? When you do that, as opposed to if you have a small K value, and when you multiply it by your concentrations, you're going to get a kind of a lower number. All right, now we did that. Why don't you determine the rate law with the orders, what the overall order is, and what is the value of the rate constant. So using this experiment, why don't you give it a go? What you have here? Okay, let's take a look, see how you're doing. So we'll start with the sort of generic rate law here that we're going to try to figure out the orders for. We'll have the rate is equal to K. Remember, again, it is only our reactants involved. So we'll call this guy X, and we'll call the I minus Y in this case. So again, we're going to look at our table, and we want to pick, again, two entries where one of the concentrations stays the same and the one varies. So we can see here experiments 1 and 2 will accomplish that. We'll keep our first guy constant there and vary our second concentration. So looking at experiments 1 and 2, I again am going to actually choose the larger rate to put up on top just to try to give me a little bit more of a whole number sort of result. So I'm going to put everything for experiment 1 up on top, and then everything for experiment 2 on the bottom there. So that would give me 2.2 times 10 to the minus 4 equals K times 0.08 to the X and 0.034 to the Y. And again, that's pretty much everything from experiment 1. On the bottom, we'll go everything for experiment 2, which will be 1.1 times 10 to the minus 4, our K, 0.08 to the X, and 0.017 here to the Y. At this point, we're going to do a little math here and use sort of our same logic as we used previously. So that's going to be 2. Once again, we do not know what the rate constant is at this point, but it is a constant number, so we know that those will cancel. We do not know what the order for our first guy is, but it should be the same, so those are going to cancel. And when we do our last guy there, they won't completely cancel out to 1, but they will end up at a 2 to the Y. And again, in this case, pretty easy to see that a Y is equal to 1. Any questions on that there? That would mean the order with respect to I minus is first order. We are then going to go back into our table now and keep the I minus constant while varying our first reactant. And it looks like we could do that with experiments 2 and 3. We'll keep that guy constant and vary the others. So looking at experiments 2 and 3, again, choosing the larger rate here to put up on top. So I'm going to do number 3 up on top, and that would give me 4.4 times 10 to the minus 4 is equal to K 0.16 to the X, 0.017 to the Y. Once again, I'm going to now put experiment 2 on the bottom, 1.1 times 10 to the minus 4, K 0.08 to the X, 0.017 there to the Y. Any questions on where any of those numbers come from? All right, so that's going to give me a 4, it looks like. And once again, these K's are going to cancel. These guys here will not completely cancel, but give me a 2 to the X. These guys will completely cancel. And that means in this case, X is going to be 2, our second order with respect to our first reactant. Now that we actually have the orders, we can put it into our rate law and write our completed rate law, which in this case would be the rate, excuse me, is equal to K times the concentration of S2O8. And that is going to be to the second order, and our I minus here was to our first order. That means the overall order in this reaction is third order, right? So 2 plus 1. will give us a third order reaction actually happening in this particular case. Also means that the reactant that has probably the greatest effect on the rate is which one? The first one, the S208, right? Because it's second order. So as we saw with my made up example originally, any sort of variation you do with that guy's concentration is going to have a much bigger effect than doing it with I minus. I minus again will still have an effect, but not as much obviously as the other guy. Yes. They do not. So in this case, whenever you're going to be calculating the rate law, the coefficients from the balance equations do not represent the exponents. There's actually only one place at the very end of the chapter where we'll talk about where you can use it, but it's a very specific sort of situation. Yeah. Other questions? All right, so now that we do have our completed rate law, we could again go back to our table and we really could choose any of these entries here and we could use it to solve for the value of K. So I'm going to do that now. We're going to rearrange our rate law and solve for K, which means we're just going to divide everybody to the other side. And that will give us K is equal to the rate, and as we divide it to the other side, S2082 minus, we do need to still square it when we do that, by the way, and the concentration of I minus in this case. Now, popping in our numbers here, we will have, I'll just use number one again, 2.2 times 10 to the minus 4 molar seconds divided by 0.08 molar squared times 0.034 molar in this case. And that is going to get us here 2.2 to the minus 4 divided by 0.08 squared divided by 0.034. We'll go with a 1.01. The units here are molarity on top and bottom will cancel, but there's still 1 over molar squared seconds. Yes. And as you can see here, we have different units for the rate constant, right, in this third order reaction than we did in the second order reaction, right? By the way, hypothetically speaking, there's how many units on the bottom there? 2 M's and 1 S is 3. The previous one was 1 over MS, which are like 2 units, which is like second. I don't know if that's a thing or not. Yeah. Yeah, so it's really important as we go through, and especially with those ones where we do 0 first and second order reactions. It's really important to know which order you're dealing with. And like I said, they won't oftentimes just tell you the order. They'll give you that rate constant. You'll see the units and you need to know which one it is. And the reason you'll need to know that is, as we'll talk about, there's specific equations that you need to use if it's first order, zero order, or second order. Yeah. The very last calculations. So at this point, when you're ready to calculate the rate constant, because it should be a constant value for each of those experiments, you could choose any of the entries in the table. So I just chose one. If you went back through there, for example, and did 2 or 3, you should get the same value for K. Yeah. Other questions? All right. So that's why you don't have to go back through and necessarily do it for each one, because they should give you the same one, but you could, they're all constant, so you could choose any one and it should get you the same value. All right, let's try another one here, maybe. Let's try this one. Why not? We got 4 things to choose from. Maybe not as pretty numbers. We'll see. All right, same deal. Let's do the completed rate law, the orders, the overall, and the value of the rate constant. Look, so in this case, we do have 4 entries. It doesn't really matter. It works the same way. We're going to start with our generic sort of rate law here. So we got our rate is equal to K, our NO2 to the X, we'll call it, and our CO to the Y. We're going to approach it the same way. We're going to pick, again, 2 entries where one of them stays constant. In this case, you have a choice of 3. You could do 1 and 2, you could do 1 and 4, you could do 2 and 4, you know, so you have a few different choices. They all should really give you the same answer, so it doesn't really matter which sort of combination that you choose to do so. So I'm just going to go with 1 and 2 since it seems to be right there. So we'll just go with these. But again, if you did the other ones, you really should get the same sort of results, regardless of which one you choose. So looking at experiments here, 1 and 2, I'm going to go with number 2 up on top, as that looks like a larger number. So 0.0082 is equal to K zero point 0.2 to the X and 0.1 to the Y. We're going to then do number 1 on the bottom there, 0.0021, K 0.1 and 0.1, I believe. Doing a little math here, might not get as pretty numbers as we had previously, but it is experimental, so sometimes you don't get pretty numbers. And this case, we get something like 3.9048 is equal to these guys canceling. These guys will give us a 2 to the X, and these guys will completely cancel like normal. Now, you could just look at that and go, it's probably pretty close to 4, or again, you could do the little natural log of both sides if you want to help you make that decision. When you do a natural log of this side, the X will come to the bottom. Natural log of 2 divided to the other side. And if you did all that, I'm going to use the whole number in my calculator to do the natural log of and divided by the natural log of 2. You get about 1.97, which is pretty close to 2 in this case, right? Which, if you rounded the top guy to 4, would be pretty close to 2 as well. And so sometimes, again, because it is found experimentally, numbers aren't always perfectly pretty. But again, that is sort of how you would do it. And that's close enough to round to the whole number in this particular case. Yeah. Questions on that one there. All right. So now that we did that, we're going to, it looks like you have just one option, I think, for the NO2. The only place where they stay constant is 2 and 3. We'll do that for you. So experiment 2 and 3. I'm going to go with this guy, which is barely larger, I guess. So that's going to be 0.0083 equals K to the 0.2X, 0.2Y. And we'll put number 2 on the bottom here, 0.0082 K, and we got 0.2 to the X and 0.1 to the Y. Again, if you divide that, technically speaking, it's not 1, but it's fairly close to 1. Again, you could do the natural log of both sides if you like. This guy's going to cancel. These guys are going to come out, and we're going to end up with 2 to the Y. In this case, Y would equal 0. Yeah, in this case. Yeah. And again, if you did the division, 0.0083 divided by 0.008 you get this 1.012195 equals 2 to the Y, a little natural log of both of those numbers there. And then divide by it to the other side. And if you do that on your calculator, you pretty much get 0, just in case you're not sure. You get like 0.017, which I'm going to call 0 in this case. Yeah. So again, if you want sort of a natural log root, it might require a little bit of rounding. And that again is close enough, obviously, to 0 to round. Yeah. Question on that there. That means that we now have our rate law, which would be the rate is equal to K times NO2, and it is squared, I believe, on that guy. And our other guy is to the first 0, which means you don't necessarily have to put it in there. Yeah, so you can leave the rate law just like that. By the way, if I put it in there and wrote it like this, is that correct? No, because that implies CO has an order of 1. Yeah. So if you do want to write it in there and it is 0 order, you need to make sure you write the 0 or leave it out. So you got to do that. Again, if you just put nothing there, it's assumed to be 1. And obviously that would be incorrect in this case. So you can write it in, but you got to make sure you put the 0 in that particular case if you do so people know that it's not first order. All right. So now that we have that, we could solve for our value of the rate constant. And if we do that there, squeeze it right there. So our K in this case would be our rate divided by our NO2 squared. And again, you could choose any one you like. So we'll go into the first one there, and that's going to give me 0.0021 molar seconds divided by 0.1 molar squared, and 0.0021 divided by 0.1 squared. Going to give me a 0.21. Units here would be 1 over molar seconds. Yeah. As this guy and one of those guys will cancel, right? Still leaving us 1 on the bottom. And this is, again, the units typical that we see with an overall order of second order in this case, right? As it's 2 plus 1, 2 plus 0 equals second order. Question on that one there. All right, let's do one more here to finish it up on, I think. All right, same thing, rate law, rate constant, orders, overall order. See what you come up with. It's actually not a dumb question. Probably half of the people didn't even notice that, right? So you do need to include the times 10 to the minus 7 on those numbers, right? So sometimes people miss that part of it. The good news is if you miss that part, you'll be okay to the very end. Then you'll be off, but then you'll be okay on the orders, but you will not be okay on that. So you do have to include that in there. See, most people missed it. I'm telling you, it always happens. Yeah, so this is an important part right there, actually. As was question mentioned, it is actually quite important there, especially at the end part, when you're calculating the rate constant. Otherwise, again, you're going to be off by that factor. So here we're going to do the same thing. We're going to go with our rate law here. That's going to be our K. We're going to go NH4 plus to the X and our NO2 minus to the Y. I'm going to look at this and see, looks like 1 and 2 looks like a good move. So I'm going to go experiments 1 and 2. And again, take the 32.3 times 10 to the minus 7 on top. And I'm going to do our K 0.06 to the X and 0.2 to the Y. And again, we're going to go with the first guy there, which we also would want to times 10 to the minus 7. Again, if you left that part off because you're dividing, it will come out the same. But your K value at the end, again, will not be right. And this. So doing that there, going to get us 32.3 to the minus 7 divided by 10.8 to the minus 7. Going to give us really 2.99. That's pretty close to 3. So I'm just going to round it in this case. Those guys are going to cancel. These guys here is going to give me 3 to the X, and those guys will completely cancel, which means in this case, my order with respect to the NH4 plus should be 1 in this case. Again, if you did a natural log both sides with a 2.99, you'll get pretty close to, again, 1 on the round when you do it. Now coming here, we're going to go with 3 and 4 here, which is constant. So experiments 3 and 4. Going to go with this guy up on top, which is the larger. So 21.6 times 10 to the minus 7 equals K 0.2 to the X, 0.04404 to the Y. Going to go with the other guy there on the bottom. So that's going to give me, I believe there are 2, if I'm not mistaken. And those guys are going to cancel. These guys will completely cancel. That should give me a 2 as well, which means my Y is going to equal 1 in this case. That means that my completed rate law will look something like this. The rate is equal to K NH4 plus to the first order, NO2 minus to the first order. That also means that my overall order here is going to be 1 plus 1, which would be a second order reaction. Yeah. Any questions on that so far? Now that we have that, we can solve for our K. We'll rearrange. The rate will equal our NH4 plus and our NO2 minus. And this is the point where if you ignored the times 10 to the minus 7 part, this is where your number is going to be off, right? Because you don't have that. So we want to make sure we don't ignore any of that information in those titles. I'm going to go with the very first one to put in there. So 10.8 times 10 to the minus 7 molar seconds divided by 0.02 molar and 0.2 molar in this case. And that's going to give me 10.8 to the minus 7 divided by 0.02 and divided by 0.2. And that will get me a rate constant of 2.7 times 10 to the minus 4. Unit-wise, molarity on top and bottom will cancel, giving us 1 over molar seconds, which we've seen a number of times for our second order reaction overall. Yeah. Yeah, so when you're going to solve for K, you could choose any of the entries, but you have to choose all of them together. You can't mix and match, otherwise you will get the wrong answer. Well, yeah, I could have for this one, I think I did this one, I think when I was doing it, right? The top one. So if we would have put that in there, that to the 0 power would equal 1. So since I didn't actually include it in my rate law at all, the CO, then I didn't need to put it in there. Yeah.
Two values that were like same in the one.
Yeah. Yeah, so definitely on the K, when you go back in it, and again, you can choose 1, 2, 3, or 4. You just got to keep all the entries that go with that experiment because that's where the rate's from. So yeah, that's why I kind of do the top all at once and go back and do the bottom all at once. That way I'm putting in the right numbers as you go. Yeah, you don't necessarily have to do large on top. You could do the smaller. It just gives you more decimal numbers versus whole numbers. So for people, the whole numbers sometimes easier to see. Yeah.